will be, the same applied pressure will be 100 times smaller. So now pressure-driven flow is not such a good idea for very small systems. Now, two other types of flow, electroosmotic flow and capillary pumping, and I will show you what that is, do scale better. Okay, electroosmotic flow. How do you do it? Well, basically, you move liquid by electrical forces, and that's the word here, body forces. Well, a body force is the force that you exert on the whole volume. It's if you've got an invisible hand, and with the invisible hand, which is the force you exert, you drag this little volume. So it's a force on the entire body. Pressure force was a force on an area. But this is a force on a body. So with this electrical body force, you will move liquid. And here is our Navier-Stokes equation again. So this is the viscosity term. That's the pressure term. And now there's a new term here. That's that body force. And what is it? Actually, the charge density in Coulomb per cubic meter. So the amount of charge in coulombs per volume times the electrical field. Now, if you look at the units, if you would do that, you can do that at home, you will find out that Coulomb per cubic meter times volt per meter, then that works out as Newton per cubic meter. So again, it's a force on the body, it's Newton per cubic meter. Just like the pressure gradient was Newton per cubic meter, this one is Newton per cubic meter. So, if I got somewhere in my liquid a charge density, one way or another, an electrical field will move the liquid. So, but how do I do that? Because let's say I got water and I put salt in, I get chloride ions, I get sodium ions, but they will move, distribute themselves equally through the liquid. And nowhere I will get a place where all the sodium ions sit together, so I can exert some force there. Because actually all the sodium ions will repel each other, and they want chlorides in between. So I get a uniform distribution of ions, and almost never, just by a very small chance, I get some 2 plus 2 sodiums together, but they will quickly go away from each other again. So in normal liquid, any volume I take is always electroneutral. So would you guys know where in a channel can I find a net charge density? Where would I find it? If I got a tube with liquid, would there be anywhere in the tube be some location where I would find some fixed charge? Sorry?
The walls.
At the walls. Why?
Because the tube is charged also.
Why would the tube be charged?
Also an electrical.
Because the friction between the tube and the walls, and then the walls will be charged
By what process, by what mechanism will the walls be charged? By friction. Can be sometimes, yes. But indeed, it's true what these guys say. So at the walls you can almost always find charge in systems. And friction can sometimes be the cause, but most of the time it has a chemical reason. So if I got a piece of glass, the glass has silanol groups, SiOH. Now the chemist will know that SiOH is an acid, and it can get rid of one H, dissociate one proton, and you have SiO minus. And the SiO minus sits on the wall. So it gives you a negative charge density, Coulomb per square meter, at the wall. That means, at the wall, I will get a negative potential. Negative electrical potential due to the presence of this whole sheet of charges. Of course, a negative potential attracts positive ions. So all the positive ions in the solution will be attracted by this negative potential. Not only the protons that were dissociated, but also sodium ions in solution, potassium ions, whatever. So we get a sheet of positive charge which sits very close to this negative charge at the wall. And by the presence of this sheet of positive charge, my potential, of course, goes up because positive ions are present there. So making the potential higher. And finally, in the solution, I will get, again, a situation where I have equal amount of positive and negative ions. Now this whole ensemble is electroneutral because I started off with electroneutral glass and with the electroneutral solution. I dissociated the protons from the wall. They went somewhere in the solution, but there were just a few. In the solution were many more, sodium chloride, for example. I will find some sodium opposite to the wall. But the negative ions surplus and the positive ions surplus in both places just are equal. So net, no charge. But a distribution here, negative, positive. This Z potential that I got here is the place, so normally this first layer of positive ions is so strongly attracted by the wall that they don't move. And only when the liquid starts moving, I can get to know about the potential that the wall has, because I have some characterization methods. That's called the Z potential. So in a way, the Z potential is determined not by the charge on the glass, but by the charge on the glass minus the charge of this first layer of ions. Okay. And this Z potential typically is 50 millivolts or 100 millivolts. So if you drink a glass of cola, Coca-Cola, or beer, or something, water, at the inside of your glass will be a potential of about minus 50 to minus 100 millivolts. And you will drink slightly positively charged solution next to it. It's marginal. There we go. So, anyway, so a chemical reason. Okay, I told all that. So, if I have an electrical field there, I will exert, of course, a force on the negative ions, but they are on the wall and they can't move. But these guys can move, so this is called the diffuse double layer. That one is called the stern layer, so they are almost part of the surface charge, so they can't move. But these guys, in the diffuse double layer, can move. There is the slipping plane where the liquid can slip. And so I have a certain charge density in this diffuse double layer, and the electrical field exerts a force on this charge density. That's the force. Charge density in the electrical double layer times the field. Now, the zeta potential there is an important quantity because the zeta potential there determines how much charge I got in the diffuse double layer. Now that's, I already told all of this, what we find here, the electrical force is equal to the charge density in the electrical double layer times the electrical field. Bulk liquid is electroneutral. There are just as many positive as negative ions. The charge density in the bulk is 0. That by the electrical force on the liquid there is 0. However, the force on the separate positive and negative ions exists. So positive ions will move towards the negative potential, a negative electrode I got over there. Negative ions will move the opposite direction, so there will be a current in my liquid. Sure. But there is no net force on the water molecules because just as many positive guys move in that direction as negative guys in that direction. So there's no net force. The net force only exists close to the wall where I have this net charge density. There I find just a surplus of positive ions. And that surplus of positive ions will take the liquid along. Now, what do I get? Well, it's like a pincer movement. So as if I take a pincers with this, and I move with a circular set of pincers, pincetten, I will take the liquid close to the wall, and exert the force on it. And the rest of the liquid will move along by viscous coupling. So it is dragged along by this thin layer of moving liquid at the outside of my tube. That means I get a very nice profile of my flow, a plug profile. I just take the liquid at the wall between my fingers, just very close to the wall, and move it. Different from pressure-driven flow, where I had a parabolic flow profile. So that's quite nice. It's a good way of pumping. Because if I make my channel smaller, now the flow rate is equal. Because the charge density doesn't change when I make my channel smaller. So the force is equal. So, and I will drag just as easily the liquid in the middle as in the case of a large channel. Wonderful. So I have a pumping method that doesn't give me less pumping velocity when I make my channel smaller. Electro-osmotic flow, this is called. And it has a plug profile. So here you see, if I have a plug over here, and I move it by electroosmotic flow, it's still a plug over here. No parabolic flow profile. Just diffusion in that direction. Now, we will do that tomorrow in more detail. But if we calculate the electroosmotic flow velocity, we find it's proportional to the electrical field. Of course, that determines the force. Inversely proportional to the viscosity. That's kind of logical because there's still the friction. You know, I exert this force, but there's still liquid. I have to work against the friction of the liquid. And it's proportional to the dielectric constant of the solution. You can believe that. And that's a Z potential, this potential close to the wall, where the liquid slips. This factor, prefactor to the electrical field, is called the electroosmotic mobility. So the electroosmotic velocity is proportional to the electrical field with as proportionality factor the electroosmotic mobility, mu. It's the Helmholtz-Molokhovsky equation from about 100 years old now. And here the electroosmotic mobility is plotted as a function of pH for Pyrex, silica, and Teflon. And you find that with increasing pH, the electroosmotic mobility increases. Why would that be? Who knows? What do you think? When I told you about surface charge.
And some more charged ions.
With increasing pH?
Increasing acidity,
Yeah, and what does the acidity do?
negative charges and on the walls.
So why do I get more negative charge at the wall with decreasing acidity?
Because the wall releases more H+.
Yeah. So if it's like a titration, you know, for the chemists amongst you. So if you increase the pH, you take more protons from an acid.
Okay.
And in this case, the acid is at wall. So the SiOH will be deprotonated more strongly with increasing pH. So you find more negative charges at the wall. So more counter charge in the electrical double layer. So a higher electrical force. So a higher electroosmotic flow velocity. The case of Teflon is different. Nobody knows really why Teflon exhibit this behavior, but they think because Teflon has it can't ionize Teflon. It's like a fatty stuff, you know. But people think actually OH minus ions adsorb directly to the surface, so it's a question of adsorption of OH minus ions in the case of Teflon. It gets a negative charge. Okay. And it has a plug profile, so that's what we write down here again. Very nice. Well, now, electroosmotic flow. Tomorrow I will tell a little bit more about it. Now, capillary forces to move liquid. That's also, so we have pressure-driven flow, we had electroosmotic flow, and now capillary forces. So to introduce capillary forces, I first need to introduce the concept of surface energy. Now, here we have a droplet of liquid. And in it you find I've drawn two molecules, and one sits at the boundary of the droplet, and the other one is in the middle. And you can see that the molecule in the middle has interaction with all molecules around it in a whole 3D volume. The one at the wall only has interactions with half of the molecules, only the ones under it, but the ones at the top are absent. So the energy of the one that sits at the wall is higher because it would like to be in the middle where it can interact with all molecules, but it can't. So it would like to go in, but it can't. That's why droplets tend to make their surface as small as possible, because creating surface for droplets costs energy. The lowest energy state is the one where it has minimal surface, which means a sphere. Okay, now that's surface energy. So it costs energy to create a surface, because we have less interactions as molecule. So the surface energy, often people use the gamma, has units joule per square meter, energy per area, which is the same as Newton per meter. Joule is Newton meter. And for water it's about 0.07 Newton per meter. For metals it's actually a lot higher. For example, it can be 1 or 2 joule per square meter. So that's why one of these doesn't sink, because it costs energy to create more surface here. And the weight of this animal is so low that it can, that the extra curvature that you get here weighs up against the force of gravity. Now, we can do this for a liquid droplet in gas, and then we got the surface energy of the liquid-gas interface, but we can also do it for a liquid in a liquid. And then liquids and the molecules at the perimeter, in that case, have interactions with both liquids. So it's not as bad as here, so it will normally be a little bit lower energy. We can do it for liquid and solid. That's another interfacial energy. And for gas and solid. So any interface, you can write down how much energy it costs to create the surface. Now, if you put a droplet on the surface, then you have to do with 3. There is a balance, you know, how much the droplet spreads comes from a balance between all the surface forces involved. So that is liquid solid, liquid gas, and solid gas. The droplet will start spreading, and if the droplet can spread freely, so if there are no little bumps in the solid, somebody can get stuck. Now, then the drop will spread until the energy gain is 0. So it wants to gain and it wants to get lower in energy, relax to the optimal state. And so, let's say that's the energy gain, dW, so the energy W in this case. Now, we know we have surface energy, which is joule per square meter. So all we need to do to get the energy of the system is to multiply the joule per square meter with square meter. Now, in the case of a droplet, which is circular, it has a certain perimeter, which we will call L. So the length of the outside line of the droplet. That's L. And dx is if the droplet gets a little bit larger, so with an amount dx. So that's the increase of the surface. Now, when we want to find, let's say, the situation where this one, any increase of the size of the droplets doesn't decrease the energy anymore. Now, what happens if the droplet gets larger? We will gain solid liquid energy, because we get a little bit more contact area between these two. So it is gamma solid liquid times the area increase. But we will lose solid gas, because solid liquid will move onto the solid gas one. So it's solid liquid minus solid gas because we lose that one. And then we'll gain this little bit of interaction space between the liquid and the gas. So now this is the length of liquid gas contact. And actually when it moves a little bit out, this little bit is added. If this angle is theta, then the bit that we gain of interaction area between liquid and gas is dx times the cosine of theta. That one is dx times the cosine of that angle. So that's another one that we need to add. So we get surface energy solid liquid minus solid gas, that disappears, and liquid gas times cosine theta appears. Now, and contact angle theta, that's what we are interested in, the one at equilibrium, that will occur at the minimal energy. So this again is the equation we just derived. Well, if that one is 0, then this one in the middle must be 0. That means we can derive the contact angle in equilibrium. And it will be equal to that expression. So the equilibrium contact angle actually is a function of the interfacial energies of our three interfaces concerned. Okay, now there was a long introduction to get to capillary forces. So, because what happens when liquid fills a channel? Now here we got a channel which is formed just by two plates, and liquid moves in between these two plates. Let's say they're glass plates. So there I have a line, there I have a contact line, and the water actually wants to wet the glass. So that's a capillary force. Now, when we have two parallel plates, that contact area, when liquid moves in, doesn't change. So the liquid gas area is constant because the distance between the two plates doesn't change. So now the change of energy when the liquid moves in between these planes is just equal to the increase, let's say, of the wetted surface. So we remove solid gas area and we add solid liquid area. So the gain of energy is the gain of area, which is the length times the amount that it moves forward. So that's the area that we add. So it kind of shifts into the surface. We got two areas that are created, one at the top, one at the bottom. So it's 2 times this length by the distance over which it moves. That's the area that we add. Solid gas disappears. This one is wetted. Solid liquid appears. So the energy gain of the liquid when it moves in is the energy of the solid liquid, the solid liquid interfacial area energy minus the solid gas interfacial energy times the area we create. Okay, that one we just derived is equal to gamma liquid gas times cosine theta. So we can replace that one by gamma liquid gas cosine theta. Then capillary force is energy divided by distance, or energy is force times distance. So the capillary force, the force that draws this in, therefore is this simple expression. 2 times the length, so one length over there, one length over there, times the interfacial energy of liquid gas, times the cosine of theta. Okay, now so we derive now a very simple expression for the force that draws a liquid in between 2 parallel plates. Wonderful. So we can work with that. From it, you can calculate the pressure here. So basically, pressure is force divided by area. We know the area here because the area is length times height. So to get the pressure, we divide the force over the area. Here we had length. We divide by length times height. That means for the capillary pressure, we end up with the gas-liquid interfacial area times cosine divided by height. That means that the capillary pressure, if I make my system smaller, becomes lower and lower. And that's interesting because if you make small systems, if I take a height of 1 micrometer, I will find that the capillary pressure is -1 bar. If you make it 100 nanometers, you will find it's -10 bar. If you make it 10 nanometers, you will find it's -100 bar. Now, then people say, okay, well, how can I have a pressure of -100 bar? You know, the lowest pressure I can get is 0 bar. But liquids, you can put them under tension. So if I take a liquid, I put it in a very small, in a space where it wants to wet, it will be pulled apart. Yeah? And so the water molecules will hold hands, of course, but they will have tension in between. And that tension at the front, if I have a moving liquid front, those ones at the front, they want to wet the water, they will drag the other ones along.